Okay, let's unpack this. For decades, right, there has been this single ironclad commandment in software engineering.
The one we all learn on day one.
Exactly.
Yeah.
We treat it almost like a religious text. Thou shalt not divide by zero. It's seen as the original sin of computation.
It is.
We've been trained to see this rule as this absolute safeguard. It prevents crashes, it prevents corruption. But what if that safeguard is actually a self-imposed prison?
Mm.
What if that constant systemic need to check for a zero denominator, that little if to NDO check, is the very thing draining performance from every high-speed processor on the planet?
It's an invisible tax, a huge invisible tax on efficiency.
So today we're doing a deep dive into the sources, talking about what they call the revolution of the denominator. Our mission is to unpack the shift that allows for truly high-performance, branchless computing.
And that means code that just flows. No stopping, no second guessing.
No forcing the CPU to stop and make a decision.
And this isn't some abstract theory. This deep dive, it impacts you directly if you care at all about system speed or throughput.
Right.
This decision to check for zero or not, it's costing us CPU cycles globally. And it's a choice driven by math, not by the hardware itself.
So let's start by defining that tax.
Yeah.
We're taught to be, vigilantly defensive about this. A zero denominator isn't just a possibility, it's a catastrophe.
An immediate failure.
Walk us through the tangible performance penalties we're paying for that vigilance.
Well, the first thing is just the sheer redundancy. The sources call it the double check tax, which is perfect.
Okay.
Because of this historical phobia of silent errors, no layer of software trusts the layer below it, so we end up checking the exact same condition, that if den equals, over and over again.
So where does this pop up? Where do we see these redundant checks in a typical software stack?
You see it in at least 4 separate layers. Let's say you have a simple financial app using a fraction object. First, the UI layer validates what the user typed in. Second, the business logic checks the variable before it even tries to do a calculation.
Right, makes sense.
Third, the constructor for the fraction object itself checks the values when it's being built, trying to stop an invalid object from even existing.
And then a fourth time.
And finally, the core mathematical operator, the addition, the multiplication inside the object, it does its own check, just in case.
So 4 identical checks, one after the other, all just burning clock cycles because of a lack of trust between layers.
It's pure systemic waste, but that's just the entry-level problem.
So where does the real performance killer kick in?
That's the pipeline flush. This is where the money is truly lost. Modern CPUs, they rely completely on something called speculative execution.
They don't wait for the result of those if statements.
No, they gamble. The chip guesses the outcome of the branch. It usually assumes the denominator is not zero, just to keep its internal instruction pipeline completely full.
So the CPU is always trying to work ahead, betting that everything is normal so it can maximize speed.
Exactly. It's an incredible piece of engineering, but it's all designed for throughput. And that all falls apart when the chip guesses wrong.
A branch mispredicts.
Right. The CPU guessed the denominator wasn't zero, but it actually is zero. And that's when the catastrophe happens.
What happens?
The entire instruction pipeline has to be flushed. All that speculative work, maybe dozens, even hundreds of clock cycles worth of work, it's just gone.
Instantly thrown away. And the CPU has to start over from scratch.
From a dead stop. In high-performance CodeThink scientific simulations, data rendering a mispredict can cost over 100 clock cycles per failure.
And if you're running millions of operations a second, that small tax on every wrong guess.
It adds up to massive system latency and a huge power drain.
And this gets even worse when we talk about parallelism, which is, standard now. This is the SIMD issue, right? Single instruction, multiple data.
Correct. The whole goal today is massive parallelism.
Yeah.
Processors use these SIMD units to work on big vectors of data all at once, like 8, 16, or even 32 fractions simultaneously.
So the CPU wants to line up 16 operations, hit them with one command, and then move on.
Absolutely. SIMD units hate branches. They are built for one thing: pure straight line execution. The second you put an if statement in that math loop,
You kill the parallelism.
you destroy it. If just one single zero denominator shows up in that vector of 16 fractions, the processor has to abandon SIMD. It has to stop and check each one individually.
So that 1 0 doesn't just stop one operation.
It grinds the throughput for all 16 to a relative halt.
Wow. So the rule we made to prevent a crash is actually creating this massive systemic latency at the most critical hardware layer.
Exactly. The problem isn't the zero.
It's the math. It's how we conceptually treat it.
That is the conceptual leap the sources insist we have to make. All our defensive programming, this whole idea of division by zero being undefined, that's based on standard arithmetic.
The real number line, what we all learned in school.
Right. And in that system, the line goes on forever, but that one point, division by zero, it's a singularity. It's a gap you mathematically cannot cross.
And that gap, that undefined state, is what forces the CPU to halt and flush. It can't compute across a discontinuity.
Precisely. If you want continuous, uninterrupted computation, you can't have these mandatory gaps. So the solution is to pick a different mathematical framework, one that handles it gracefully.
We have to move to projective geometry.
Specifically, the real projective line, or math BRP.
Okay, projective geometry sounds a little intimidating.
Yeah.
How can we visualize the difference for someone listening? Why is this better?
Think of the standard number line like an infinitely long open road. It goes to positive infinity in one direction, negative infinity in the other.
Two separate ends.
Yes. In projective geometry, you fundamentally change that. You take those two separate infinities and you join them. You add a single unified element, the point at infinity.
So you're taking that straight line
Yeah.
and closing it into a circle. A loop.
That's a great way to think about it. An analogy I like is a classic needle gauge, like a speedometer. As you accelerate, the needle moves up toward its maximum, let's call that infinity. But if you could somehow keep going, it would instantly wrap around and approach zero again, but from the negative side.
Ah, so you've eliminated the gap. There's no hard stop.
You've eliminated the discontinuity, and the crucial mathematical insight this gives us is that division by zero is no longer an error.
It's a well-defined operation.
It is. If you have any number, x, that isn't zero, then x divided by zero is just that unified infinity. We've shifted from generating a fatal error to generating a meaningful, manageable result.
The only thing that's still a problem is 0 divided by 0.
Correct. 0 over 0 is still indeterminate, or what we call nan, not a number. But by accepting infinity as a valid output, you eliminate the vast majority of those branch mispredicts.
You stop asking the math to raise an error every time it sees a zero denominator.
Which is the real choice here, isn't it? Do you prioritize the mathematical purity of standard arithmetic, which forces a crack?
Or do you prioritize the continuous throughput you get from projective geometry?
It's about using the right tool for the job. You stop asking the math system to do the job of the application logic.
Okay, so if we adopt this view, it completely changes how we engineer software. We move away from defensive programming toward this new standard, a contract for high performance.
That's right. The contract is simple. The data structure is just for math. The application logic is for interpreting the meaning of that math. It gets rid of the nanny state of protective checks inside the TUP itself.
But I had to challenge that first pillar. No constructor checks. That just flies in the face of decades of best practices. Are we really just asking programmers to trust that the data coming in isn't garbage?
We're asking for engineering discipline at the system level, not stuffing checks into a low-level data object. The constructor of something like a fast fraction has to trust the caller, implicitly. It just assigns the values.
And the check for whether a zero denominator makes sense.
That check happens earlier, before the object is ever created. If it's semantically invalid for your application, you stop it at the door.
Okay, so if the object is created, naked, what are the other pillars that make this system robust?
Second, we define unsigned infinity. We accept a zero denominator is a valid state. Third, and this is critical, is sticky nan.
Sticky nan.
0 divided by 0 is nan. And any operation you do with a nan add, subtract, multiply must result in another nan. It propagates.
So the corrupted data point is automatically flagged and tracked through all of calculation.
Without needing a single conditional check at every step.
And the fourth pillar is where the real safety net is. Gateway validation.
Precisely. All the semantic checks, does this number actually make sense in the real world? They move to the system's boundaries, and that frees up the core computation engine to just run pure and branchless.
So what does this branchless code actually look like? If you rip out all those if statements, how simple does the math get?
It becomes stunningly simple. The code for, say, an addition operator is just pure straight-line algebra. No jumps, no exceptions, no conditional logic at all.
The CPU just gets an uninterrupted flow of instructions.
Okay. It runs at the theoretical limit of the hardware. It maximizes SIMD because there's never a reason to halt the assembly line.
And validation checks, like is some finite or does non, They become explicit optional things a programmer can ask.
Exactly. They become queries, not mandatory gates that stop everything. The responsibility hasn't vanished, it's just been moved and made more intelligent with the gateway pattern.
You're moving the security guards to the front and back doors of the building.
That's the perfect analogy.
Okay, so let's walk through an example. A user submits something that results in calculating 5 divided by 0. How does this validate, compute, sanitize flow work?
Right. That input first hits the inbound gateway. The gateway does the semantic check. For this specific task, does a 0 time divisor make sense? If not, it blocks it right there.
But let's say it's allowed to pass. The potentially problematic 5 over 0 goes to the computation engine.
And the engine does its branchless, high-speed math. 5 over 0 is instantly calculated as infinity. And crucially, the engine keeps processing millions of other transactions. It doesn't halt.
And then that result, infinity, hits the outbound gateway, the final layer of protection.
Yes. The outbound gateway sanitizes it. It does an explicit check. Is this result nan or infinity? If it is, the gateway turns that mathematical state into a domain-specific action.
Like logging an error
Or showing a friendly message to the user like, result is out of bounds, before passing clean data to the database.
This sounds absolutely critical for any industry where nanoseconds count. High-frequency trading comes to mind immediately.
HFT is the perfect case study. The stakes are incredibly high. A 100 nanosecond delay from one branch mispredict, that pipeline flush we talked about, can literally cost millions of dollars.
They need throughput above everything else.
They need throughput, not immediate crash traceability.
So if a little glitch in market data causes a 0 denominator in a price calculation, what happens in the old system versus this new one?
In the old way, the system that favors traceability, that 0 causes an immediate exception. The trading app crashes.
You know exactly where it happened.
You do. But the entire trading pipeline for that venue is halted while the system restarts. That's an unacceptable business failure.
And under the new standard.
That 0 denominator is instantly calculated as infinity or nan. The system doesn't stop. The outbound gateway flags it as a manageable business exception. It might discard that one calculation.
But the whole system keeps processing the next million trades.
Without interruption. A crash is a disaster. A NAN is a managed exception. The system is faster and paradoxically more robust because the math engine never has to stop.
So if we synthesize this whole deep dive, the real philosophical shift is this. We have to stop asking our low-level math types, our fraction classes, to act like nanny.
Yes, stop asking them to police the semantic meaning of the numbers they're holding.
That's not their job.
Not at all. A low-level math type should do one thing: efficient math. The best math for the job, which is math BBW11. The responsibility for meaning belongs higher up in the domain logic, in the architecture, at the gateways.
We have to trust programmers to be engineers.
We have to.
So the forbidden 0 is really just a relic, a dogma from an era of different hardware constraints. By embracing this contract-based design, we build systems that are simpler, way faster, and more robust all at the same time.
Indeed. And the source material ends with a challenge that really brings it all home. It's something for you to think about the next time you see a division by 0 check-in code. Ask yourself,
Am I doing this because it's necessary for the system to be safe? Or am I just following a rule I never really questioned?